using closures that capture their environment. Now that we've introduced iterators, we can demonstrate a common use of closures that capture their environment by using the filter iterator adapter. Okay? We're going to talk about filters on iterators. The filter method on an iterator takes a closure that takes each item from the iterator and returns a Boolean. If the closure returns true, then the value will be included in the iterator produced by filter. If the closure returns false, the value won't be included in the resulting iterator. I see. So what they're seemingly saying here is that on an iterator, we can use a method called filter, which is an iterator adapter, and then within it we can put a closure that's going to check the item and return true or false. If we want to keep it, true. If we don't want to keep it, false. And it should be noted that everything that we keep is going to be passed along to the collection that we're going to create post this. In listing 13-19, we use filter with a closure that captures the shoe size variable from its environment to iterate over a collection of shoe struct instances. It will return only shoes that are the specified size. Alright, coming down to the code, let's see what we have here. Looks like we can erase most of this. Yeah, or not. I mean, you can keep it. So, let's talk about shoes. So we're putting derived here at the top, right? Derive, not derived. And what I believe this is doing, we have a partial equal, right? And we have debug. If I recall correctly, this is applying these methods on our struct because they're simple and we can get the standard library or Rust itself to do it for us instead of us writing them out. Thank you. So let's create our struct shoe. Size is U32 because you can't be negative, so might as well just be unsigned integer. And then the style is a string. Makes sense. And we have a function shoes in my size. I'm not the greatest typer right now, but I'm working on it. So we pass in shoes, which is a vector of, you guessed it, shoe. And then we pass in shoe size, which is a U32. And then what we want to return here is a vector of shoes that are our size. And then we create this body. So we say shoes because we have the vector of shoes into iter, which takes ownership of everything that we're about to act on, all the items. And we have a dot filter, and this is where we pass in the closure, S for shoe, and if shoe dot size is not equal to our shoe size, the one that was passed into this function, then we don't want it. And because it's still a iterator adapter, I mean it's filtering, but it's not consuming anything, we still have to call collect. This does, oh, I see, I understand. We're calling collect, and then the item that is returned by collect is what we are returning here. That makes sense. And then we write a test for it, put that at the bottom. So create another test block. test function filters by size. So we say let shoes equal a vector, and in this vector let's put some shoes in there. So shoe size, they're a 10. I'm a little bigger than a 10, but okay, a 10. A style, and then from a style we'll say string from, and we call this one, this is going to be sneakers. Our next shoe is going to have a size of 13, very large shoe, much bigger than my feet. I can't wear you. And they're going to be sandals. Size 13 in sandals. Wow. Okay. And sandals. Now next, the last shoe they have here is closer to my size, 10, space. And the style is string from, and it's a boot. So that makes sense. And then let in my size equal shoes in my size 10. Shoes in my size, that's the function that we created. We're going to pass in shoes, and now we're filtering for all the shoes that are of size 10. And then since this is a test, we have to assert what we got back is what we wanted. So we assert equal. We have in my size, and we want that to be equal to a vector of 2 items, and the 2 items that were in my size. And I'm just going to copy them. Copy. One. 2. Back to the bottom. Back that over here. That looks about right with the exception of U. And let's call cargo test. And I wrote something wrong. Dot filler. Well, you need a T. You definitely need a T. And all of our 3 tests have passed, including the one we just wrote, filters by size. Yeah. Moving onward. The shoes in my size function takes ownership of a vector of shoes and a shoe size as parameters. It returns a vector containing only shoes of the specified size. In the body of shoes in my size, we call into_iter to create an iterator that takes ownership of the vector. And yeah, that is something I noted earlier. That is right here. Takes ownership of it. So the shoes that were in the original vector that were being passed in are now owned by this new collection that was created by collection, which is the vector that we are returning. So it's still good to act on those shoes later on. Then we call filter to the adapt. Then we call filter to adapt the iterator into a new iterator that only contains elements for which the closure returns true. And that is here. So this is the filtering process. We have filter. we have a closure. Oh, I don't want to change change any of that. I just moved the line. No. Alright, let's go back. Let's write that in here again. Filter. Put that there, and you should be fine. So we have our filter here, and this is our closure. We have S, and then here we have the expression that is used to check whether or not shoes are in our size, and then returns a Boolean. If true, then keep. If false, then discard. And then let's see what else they have here. The closure captures the shoe size parameter from the environment and compares the value with each shoe size, keeping only shoes of the size specified. Finally, before we get to finally, let's see what they're talking about. So here we reference shoe size within this closure. And what they want us to note is that this variable shoe size is being captured from outside of the closure because it comes into the function, but the closure itself does not define it. Understood. This means that our closure is capturing information that is outside of our closure, which is in the closure environment. Right there. Finally, calling collect gathers the values returned by the adapted iterator into a vector that's returned by the function. So then we call collect. This runs, quote unquote, consumes our iterators, and then returns a collection data something, struct, which in this case is going to be a vector. The test shows that when we call shoes in my size, we get back only shoes that have the same size as the value we specified. And scrolling down to our test, here's where we have that example. We had 3 shoes in the original vector. They had various sizes. 2 of these sizes were 10, 1 was 13. We called a filter on them. We only wanted things of size 10. And what we got back was only of things of size 10. Yes, it's doing what we want. Creating our own iterators with the iterator trait. Alright. We've shown that you can create an iterator by calling iter into iter or iter mutable on a vector. You can create iterators from other collection types in the standard library, such as hash maps. You can also create iterators that do anything you want by implementing the iterator trait on your own types. As previously mentioned, the only method you're required to provide a definition for is the next method. Once you've done that, you can use all other methods that have default implementations provided by the iterator trait. Alright, so here they're going over some of the little things that we have to do if we want to create our own. So earlier they told us that all we have to do is implement the next method on the iterator. That's the only thing we need. And once we have that done, we can use all of the things, all of the methods, iterator methods that have default implementations. Yeah, we just use those. It comes with it, which is nice. So now we're going to go through creating one of those. To demonstrate, let's create an iterator that will only ever count from 1 to 5. First, we'll create a struct to hold some values. Then we'll make this struct into an iterator by implementing the iterator trait and using the values in that implementation. Enlisting 13-20 has the definition of the counter struct and an associated new function to create instances of counter. Alright, so let's start with counter. And we don't have to get rid of anything. Let's just make a new one. Struct counter. Count U32 and implementation block for counter. And that's funny that it lit up. Or new associated method returns a new counter. Counter with a count of 0, and we're good. We'll create a struct, has the property count, which is of type U32, unsigned 32-bit variable. And then we have the associated function called new, which is going to create our counter, initialize. Alright, so moving onward. The counter struct has one field named count. This field holds a U32 value that will keep track of where we are in the process of iterating from 1 to 5. The count field is private because we want the implementation of counter to manage its value. The new function enforces the behavior of always starting new instances with a value of 0 in the count field. Okay, so we already know that we have this field, this one field of count, and it holds a U32, as I mentioned, and we're going to be using this to dictate counting from 1 to 5. And it's private because we don't want other people messing with it. Make sense? Next, we'll implement the iterator trait for our counter type by defining the body of the next method to specify what we want to happen when the iterator is used, as shown in listing 13-21. Let's just write this right here. Implementation block. Iterator's right there. For counter, we have to have a type for our item, and we're going to call that a U32. Okay, and then we're going to have a function next, which has a mutable self-reference. This we knew, and it's going to return an option of self item, which we also knew. That seems like boilerplate. And then here's where we put the logic or code that we care about. Self.count plus equal 1. Then if self.count 6 sum self.count else, I can finish writing else, none. Okay, so here we're incrementing count by 1. So if you notice that when we initialize count, we set it to 0. And then the first time we call next on it, it's going to be set to 1 because we're incrementing it by 1. Then while count is less than 6, we return count. However, if count is ever equal to or greater than 6, we return none. And this should give us the calling next on it. We should see 1, 2, 3, 4, 5, none. Moving onward. We set the associated item type for our iterator to U32, meaning the iterator will return U32 values. Again, don't worry about associated types yet. We'll cover them in chapter 19. We want our iterator to add one. Let me go over that real quick. So here, they're just mentioning that we have a type. We know that our iterator is going to return U32. That's what our count has. We're just explicitly stating it for our item. So here, this first sentence, they mention that the type of our iterator is going to be U32, which is pretty obvious given that our count is U32. That's the only type that we have. That's the only thing we can't return. Okay, cool. And then they tell us not to worry about this type thing yet because they're going to explain it in chapter 19. Chapter 19. Moving onward. We want our iterator to add 1 to the current state. So we initialize count to 0. So it will return 1 first. If the value of count is less than 6, Next, we'll return the current value wrapped in sum. But if count is 6 or higher, our iterator will return none, which is the if statement down here, right here, that block. Using our counter iterators next method. Once we implemented the iterator trait, we have an iterator. Listing 1322 shows a test demonstrating that we can use the iterator functionality of our counter struct by calling the next method on it directly, just as we did with the iterator created from a vector in listing 13-15. So yeah, another test just to show that this functionality worked as expected. And let's just write that down here. Test function calling next directly. Let mutable counter equal counter new, and then we're calling this a lot. So let me just write this once and then copy it a bunch of times. Ooh, we're not returning a reference. That I'm interested about. So if you notice, we have our counter, right? And we do a .next. And then here, we return sum, and we have a 1 in here. Earlier when we did this, still have it up here, we called iter, and we had to have a reference to 1 because iter only returns immutable references. So what's going on here? I do not know yet. We'll find out shortly, hopefully. Copy. Let's get this written first. Is that enough? 1, 2, 3, 4, 5. None. Okay. So I've written that out. Let's run the cargo test, and it failed. Why did you fail? And because I misspelled filter again, or I took out the T. Keeps me honest, keeps me honest. And it passed. So it's doing what we think it's doing. This test creates a new counter instance in the counter variable and then calls next repeatedly, verifying that we have implemented the behavior we want this iterator to have, returning the values 1 to 5. They are not explaining it. So let's see if we can go back and figure this out real quick. I guess this does not have to be a reference because we're not returning a reference. We're returning the item itself. Okay. I think it's just the way we implemented it. If we implemented this with references, this probably should be a reference instead. Okay. Moving onward. Using other iterator trait methods. We've implemented the iterator trait by defining the next method, so we can now use any iterator trait method's default implementations as defined in the standard library, because they all use the next method's functionality. For example, if for some reason we wanted to take the values produced by an instance of counter, pair them with values produced by another counter instance, after skipping the first value, multiplying each pair together, keeping only those results that are divisible by 3, and add all the resulting values together, we could do so, as shown in the test listing 13-23. That was a mouthful. I don't even know what I said just now, but let's just see what happens. So here's the example, right? We have a counter new. We're calling zip on it. And we're zipping it, meaning like matching it together with another counter after skipping the first one. So post this zip, we should have 1, 2, 3, 4. We should have like tuples of, hopefully tuples of 1, 2, 3, 4, 5, none. I think. And then we're doing a mapping. Wait a second. If this is skipping the first one, but this skip is on this iterator or not, actually I'm a little confused at what this does. Because the none thing, down here at the map, we can't have 5 times none. That doesn't seem right. But let's gloss over that for a second. Let's say, for example, we have 1, 2, 3, 4. We have 1, 2, 2, 3, 3, 4, 4, 5. Let's say we have that as a production of this zip, where everything is like oscillated by 1. And then we go to this map, which takes those pairs that we had, 1, 2, 2, 3, 3, 4, 4, 5, and then multiplies them together. Returns a new vector. And then that vector, we're going to check to see if any of those items within it are divisible by 3. And if they are, keep them. And after that, we're going to sum all of those items together and assert that the sum is equal to 18. Okay, so let's write that out and see what happens. Test function using other iterator trait, let me spell it correctly, methods. Let's sum u32 equal counter new dot zip, put in our second counter in here, counter new dot skip, skipping 1, dot map. That's not lined up the same way, but you get the gist of it. A times B dot filter, spell it correctly this time. We have X, and we want to see if X is divisible by 3. Dot sum. And then we're going to assert that the sum, I can put sum first, is equal to 18. So let's just run that and see what happens. We got an error, as we should. We had an error at the map portion. Did I write that wrong? Map. I did. I forgot to put that in a tuple. And now it has its types. And it said it passed, which is really curious because I want to see what's in this. Let's do collect. And it's not going to print it out. Actually, what does it say? A collection of type U32 cannot be built from an iterator over elements of type U32. That sounds confusing. I'm gonna have to take the word for it. But we know it's 18. This worked as they expected it to. This is kind of gibberish to me. I'm kind of tired going through the mental flow, figuring out the exact numbers. Meh. Anyway, Note that zip produces only 4 pairs. The theoretical 5th pair, 5, none, is never produced because zip returns none when either of its input iterators returns none. I see. So zip goes to the smallest iterator that is pairing. So like I was saying earlier, just going over this one more time, we have our first iterator, right? And it starts at 1. We zip that with our second iterator, which we're skipping the first one. So now we have our pairs, which is 1, 2, 2, 3, 3, 4, 4, 5. The theoretical 5, none is skipped because when either of the iterators returns none, that sequence, or that at least in this, that tuple in this case, is discarded. So we take what we have and then we do the map. The map is multiplying. So we have 1 times 2, which is 2. We have 2 times 3, which is 6. We have 2 times 3. We have 3 times 4, which is 12. So that's 6 and 12. That's already our 18. And then we have 4 times 5, which is 20. And that is after the map. And now we're filtering for items that are divisible by 3. And the only things that we have that are divisible by 3 are 6 and 12. So we sum those two. Everything else gets filtered out. And that is how we get to 18. I was able to do it. Cool. All of these method calls are possible because we specified how the next method works. And the standard library provides default implementations for other methods that call next. And with that, we are done with this section. We have just covered the basics of iterators. Round of applause. I hope that was entertaining. Hope it was useful. If you liked it, subscribe. Outside of that, peace.